Well, hi, good morning. Thanks so much for joining me here in my shop for what should be a very interesting session here. I think I'm going to fix this guy today. I'm going to get him working properly today. That's what I think. So I was in here last night for quite a while, ohming out this generator. So what I mean by that is I take my ohm meter, I take a look at the schematic, say to myself, well, you know, if you can test between pin 6 here and pin 7 there, you should read this resistor, 100K. And I just go through every kind of combination I can come up with, looking for an anomaly. And I spent a long time doing that. No anomaly. No, every reading I took made sense. I didn't find anything at all. So when I ran out of resistance checks, I decided, well, let's do some more voltage checks. I've never checked the output of the bias circuit. So I'm going to explain what the bias circuit is in this. It's not what you think. And I'm going to tell you, I think the bias circuit is in trouble. So there we have a rectifier right here, selenium rectifier. These things are not terribly reliable. They have a life. These things can burn up. It's a terrible mess when they burn up, so I hear. I've never had one burn up on me. As they get older and they become less efficient, they get a bigger and bigger voltage drop, they get hotter and hotter, or they don't rectify as well, they start leaking backwards, and all that stuff takes place. So the voltage check, when I check for the voltage right here, my meter jumps up and then just drifts right back to around a volt or so. Exactly what the voltage should be here, I don't know. What is going on here? So it starts off with this device up here. This thing, which is a little hard to see what all it is. There's some coils up in here. See a bit of it up in here. So you can't really look at it physically and sort out anything much about it. If we look at it on the schematic, I can explain what it is. This is the key component that sets this device apart from other sweep generators. The sweep range on this is huge, 60 megahertz or something like that. Explained before how difficult it is to make this happen, and they're using a special transformer, an Increductor, incremental inductor, Increductor. Here it is, it's all this. These coils are forming the resonant coils against these capacitors here to generate an oscillation amplified by this amplifier. That's how it's working. This coil is of great interest. This is part of the Increductor. My understanding is the iron cores of this and these guys are in contact, which means the magnetism generated in any of these is kind of shared out around them all. Now if you look at this very carefully, I blew my head off when I saw this last night. I hadn't noticed it. Where's the diode getting its feed from? Well, it's getting it from the primary side of the supply transformer, right from the hydro. I sort of assumed everything is on this side of the transformer, and that gives a certain amount of isolation from the power plug. But no, they've got a circuit in here that's right on the power plug. And comes up here, fiddles around with this diode, some capacitors. You end up with a DC current flowing through the windings here. So something about a transformer that you may not know, but I know from an experience I'm going to tell you about when I was working at the power company. We get a call. I worked for Toronto Hydro. I got a call from Scarborough Hydro calling us because we're the big guy with, I don't know, more brains maybe? I don't think so. Guys in North York Hydro were pretty smart. They had a transformer which they had just installed, this is a big 50 kVA, 500 kVA transformer. It's a big unit, you know, size of a very small car. They just installed it at a new building and hooked it up, and it was screaming at them. But it was screaming in a weird pattern. Kind of a come and go and up and down and this and that. And they'd heard something about stray current from the Toronto Transit System. That's a DC operated streetcar subway system. Yeah, extensive streetcar subway system. And they wanted to know if we knew anything about it. And so it came to me. I was the corrosion technician, and my job was to chase stray DC current coming from the transit system through the water system and hydro systems of the city of Toronto. Yeah, does that sound kind of wild? Yeah, you think chasing currents around in something like this is fun? You should try it on a city. How do these currents get in there? Well, I won't go into a detailed discussion because I'd have to do a whole video on this topic, really, to explain it well. But of course, the DC transit system is fed with DC stations. Where do they get the direct current from? They have rectifiers, huge rectifiers. These days, they're huge solid-state rectifiers, rectifying thousands of amps. So the station supplied AC high voltage, transform it down to 600 volts, rectify it. 600 volts DC runs all the streetcars in the subway. The whole system is parallel. The whole system is parallel. So every supply power station is supplying power to a parallel or a continuous set of tracks. You can think of it that way. And another station, a mile away or a couple miles away, another one. All operating simultaneously together. Again, without going into the details of why this happens. Oh, wait, I missed one part. So, of course, to maintain safety and to ensure there aren't disparate voltages in public locations, like, for instance, in the subway, as you step onto the subway train, you've got a foot on the ground and a foot in the train, to prevent there being 600 volts there or something crazy like that and killing 50 people all at once, which I don't think can ever happen, but that puts a pretty good image in your head. They would do grounding things to maintain safety. And what do you do when you want to ground something? Well, you hook it up to the hydro neutral, hook it up to your water mains. So each of these stations along the line, where the power feeders come in, water pipes come into those stations, connections are made, basically, back to the tracks. The tracks are the negative side. They're laid in the ground, so they're at ground potential. And so everything's hooked together. Everything is hooked together. This allows some of that stray current, and we are only talking about a few amps, right? Thousands of amps flowing into the subway cars and the streetcars, thousands of amps at 600 volts. A trickle finding its way through ground connections all through the city. You can find it in people's houses. You can go down to where the wire, if you live in the city of Toronto and you got a clamp-on ammeter that can read DC, go do this. Go down, find your ground wire that ties the water pipe to the hydro neutral. Put your clamp-on meter on that. Set it to DC. I have one here that would do it. This guy. This guy read DC. And you would not be surprised if you see a variation of current. You see a DC current kind of going up and down a little bit. And that's related on the location and operation of the streetcars and subway cars on the system and how they're drawing current through all this stuff. Drawing stray current through all this water mains and all that kind of stuff. If you hook up a particularly wired kind of, that's a stupid way of saying it. If you take, in the power setting, in the industrial setting, often the primary side of these big transformers are star wound. So you have a star winding with a neutral in the center, which is often grounded. Grounded by rods into the soil, grounded by bonds going back to water mains, hydro neutral, anything, everything. Well, it is a hydro neutral actually. And that wire will travel all the way to the secondary of a super high voltage transformer where there's another star connection and another ground point. Those two ground points are a distance apart. Even if it's not just ground rods, even if it's connections to the hydro neutral, there's resistances involved and stuff like that. What can happen is you can get a current flow, believe it or not, through the star neutral, through the windings of the transformer, out onto the power lines. This is DC now, traveling down the power lines, up on the poles and all that stuff. Coming through people's equipment and motors and stuff like that, and three-phase equipment, finding its way back to the ground. This current is flowing through the windings of the transformer. And if I had a chart here, if I put a chart meter on what this current would look like, it would look something, I can't hold my hand like this, it would look something like this, like it would go up, and then come down, and just completely random sort of motion. But if you chart it for 24 hours, which is what I used to do, you could see quite clearly it's active during the day, and then at night it settles down to a quiescent point, which is extremely interesting, but I won't talk about it. And then the current begins again the next day. What's happening? The streetcars are running, the subway's running. What does a transformer sound like with this kind of DC current flowing through the windings? It is screamingly loud. Okay, so I get this phone call. Oh, that's interesting. I'll come take a look. We go up to this place in North York. There's a large, brand new apartment building, like a 15-story, 10-story apartment building. Out front is the transformer vault. You go down in. Park my truck. I get out of my truck. I can hear the transformer already, and it's 65 feet away underground. Holy smokes. So we go to the vault. We're standing on top of it, and this thing is just roaring inside. And I'm panicked. I don't want to go in this vault. Down we go. And we spent a couple minutes in there because I couldn't stand it. Transformers humming away, overheating, no load on it whatsoever. And they turn to me and they go, "Do you know why this is happening?" I gave them that whole explanation. They had to pull the transformers out of there, put in a different style of transformer, and they changed the way they were doing things because their eyes have been opened to how this stray current can flow in the windings of a transformer and cause this effect. What effect? It's changing the small DC current will change the I might not get this quite right. The magnetic permittivity, is that the right word? It will change the magnetic standards of the transformer. And in the case of that one, the great big transformer actually overheated with no load. Exactly how that happens, I don't know. It has to do with currents maybe flowing in the tank walls. I don't really know exactly, but what a situation. That idea of DC flowing in the windings of an AC transformer is used in this apparatus, and that's why I told you that whole story. So they're going to put DC through here, and it's going to affect magnetically all these cores. Where do they get the DC from? They get it from here. Why do they even need it? They need it to put this into a certain range of operation, if you like. And this is a bad explanation, and I may even have it wrong because I've only read it 3 times or 4 times over. I haven't got to 5, 6, and 7 yet. So there's another, and you can vary the current here. There's an AC current flowing in here also, which is what's causing the sweep. So that's that really AC current in here affecting the magnetic condition of this part, which is being passed out into these, affecting the magnetic condition of this part, affecting the impedance of these coils, affecting the resonance point of the circuit. So make this guy more magnetic, make those guys more magnetic, change the inductance a lot in these cores, in these transformers or coils. That's the whole idea. And so to do that, they have a separate circuit, basically just a tap off the 60 cycle AC. And why are they doing this with 60 cycles anyway? Well, because it's the same 60 cycles that runs my scope, and so you can use the 60 cycles in the 2 devices. That's not exactly 60 cycles, but you get the idea. The 2 devices are locked together by the 60 cycles, so you can synchronize the operation of the 2 devices. And that's why not only this generator, a lot of generators use this trick. This one uses this trick too. The wobbler wobbles at 60 hertz. Okay, so what's the problem? Well, the problem is when I go to read the voltage here, when I put my meter on it, which we're going to duplicate because this is the starting point, the meter will jump up and then just come down to almost nothing, which strikes me as being completely inappropriate. It's a voltmeter. I was using my 10 megohm input voltmeter on it, and that's bleeding away enough current to discharge this capacitor, basically. Something like that's happening. Hard to believe. Seen it with my own eyes. Now what happens if this isn't producing the current that should be sort of the steady state current? This will be out of balance. Perhaps the magnetic situation of these is such now that they won't resonate, that nothing will work. Well, that's my hope. That's my hope, that I found the problem. Unreliable component causing me trouble. Now I'm going to repeat that test I did, find out I was wrong. The whole thing's hogwash. I told you all that nonsense about DC current in the transformer windings of power transformers for nothing. And I'm still at square one. Well, let's hope that's not the case. I'm very hopeful about this. I don't need this meter. We're going to use this guy here. Just get a cord out of the way here. Okay. Excuse me. Again, to me, this circuit looks very simple. Just looks like a rectifier, capacitor to charge up, and some resistors fooling around here. This switch switches in and out this resistor, so it'll bypass it when the switch is in the position it's in right now. It will bypass it. And that's just to somehow rebalance the amount of this current at different band settings. This is the band switch here. Are we ready? Okay, I'm going to make a ground connection here. Don't like that very much. So there's a good spot up here. Okay. Switch it on now. Just to give you the view of the dim bulb. I've also been watching this the whole time I was doing the work. Excuse me. I was watching this on my scope just in case the thing popped back to life, but no. No life. Oh yeah, you gotta get to see the scope here. Let me change my lights here. Well, you gotta see the scope. You want to see the scope, Jim? Yeah, I'm overly excited this morning because I really think I'm going to surmount this issue. Okay, she's running. Now, the rectifier's right there, positive terminal's right there. Watching the voltmeter, this is set to 50 volts, full scale. You saw it. My first time I tapped it there, I missed it. He jumped all the way up to here. Probably could have gone much higher. Then come all the way down to nothing almost. This is 50. This is less than half a volt sitting there. Take it off. Give it a moment. Let's take it back on. There it is again. As if the meter is drawing the charge out of the circuit. So that's the point last night that I stopped and said, ooh, we can start the video at this point. So this is a pretty easy thing to replace one of these. I should just go ahead and do it anyway. And generally, guys doing this work like to replace these things because the ultimate risk that they have, and often in an older, like this looks good, this one looks really good. But in other circumstances, they don't look so good. And it's good to get them out. Stick a little ordinary silicon diode in there. It's very easy to do. You get a little extra voltage. Maybe that's an issue with this. Certainly is an issue right at the moment. I guess all these resistors have been set and contrived to put the right amount of bias current through the Increductor primary. Yeah, actually last night when I was ohming this out, I got to the point where I wanted to ohm this out. I tried and tried and tried, but I couldn't do anything that gave me any impression that I was actually doing a valid test, because there's too many connections and stuff going on in this. But at one point I suddenly realized, oh my god, this could be open. If this is open, this is done. This thing's finished. Yeah, but it's not. I don't think it's open. I think the problem is here. Now it's got like, it's got yeah, It's basically a diode and a capacitor just right there. So this should really be charged up. It's a 150 volt capacitor. They're ready for something there. 40 microfarad against these big guys here. Could they be defective? Now this would short it right out, I think, if this were to have overheated resistors here. I don't know for sure. I have to study that a little more. Ah, they could be bad. Could be a couple bad capacitors. That's true. How can we figure that out? How do we know for sure it's that thing? So one way would be to replace it and move on. That's not a bad idea. Replace it and move on. It's very easy to simply take one wire off there. Oh look, there's a terminal right up here. I just could put a diode from the back terminal to the front terminal and cut the lead wire there. Very easy to do. So if I cut that wire, we can also test that rectifier. Cut that wire. Testing a rectifier like this, you got to use your power of judgment, I think, as to whether you think it's good or bad. I think the front to back ratio of resistance should be something like at least 1 to 10. Probably much better than that. So we'll just try one way. Is my meter working? Hey, you're going to work for me today. One way shows open. The other way my meter's not giving it enough kick. That's a bad sign. So this is putting out some voltage on these leads. You would think it'd be enough to overcome the forward drop on that diode. Rectifier, I should call it a rectifier. Maybe that, so I don't know, did I just prove it's totally defective? Let's stick a silicon diode in there and go from there. Okay, so I stuck a 1N4005 diode in there, which I'm sure is going to work out fine, and I'm so sure this is going to work. I'm going to show the scope. The scope is hooked up to the output here. So if any output shows up here, it's going to be on the scope. Now, is there any other big concern here? No, I don't think so. Okay, let's let it rip. This is switched on. Put on the other switch here. Let's just check a couple settings. Marker amp is on. Turn it off. We're not interested in the marker amp. When turning this off, breaks the beat plus to the oscillator plate. AC. This is the horizontal phase. Doesn't matter to us right now. Sweep width in the middle. Find attenuator in the middle. Big one times 1. Frequency we're coming out with is we'll start on band A, which is the lowest band, about 5 megahertz. Something like that. Okay, I can't delay any longer. Did this work? Oh! The answer is no. Okay. Hey, dim bulbs. Thumbs up on the dim bulbs. So, with the dim bulbs coming on bright like that, it means I've developed a short circuit in this unit. Duh. How could I have done that? All I did was stick a little diode in there. Well, the answer might be, why did the diode fail in the first place? Maybe a shorted capacitor? I don't know I don't know the rectifier died. I don't actually know for sure that it's dead. I did some tests on it that indicate it, but I'm not totally sure. What did I do here? Did I? Oh, I don't have many options to make a mistake. Positive's in the right place. Oh my gosh, I'm out of the pen into the fire. How did this happen? Well, I have no choice. Do a little more trouble. Here we go. Resistance testing again. I was so hopeful this would just be bing, bing, bong. Not bing, bing, boom. So what I want to try to do is, what am I doing anyway? Look for a short circuit that I've created in there somewhere. Now the power supply has no ground to the chassis on the primary side anywhere. So really, this could go right on the plug. Let's try that. So I'm gonna not quite sure about this. I'm going to be testing it with DC, the ohmmeter DC. I'm not sure this is completely valid, but let's see what happens. Well, that doesn't look too good, does it? 0. Let's just verify my meter because it acts up all the time. Yes, it's acting up. $12 ohms. I like the 0 better. Oh, this is just unreliable, completely unreliable. Oh, there's the 12 again. There's the 12. Okay, 12 ohms it must be. It's a crazy test I'm doing because I'm just reading. Wait a minute, let's open the switch here. Open the switch. And how does that help? Well, we know the switch works now. Well, that's great. I got no idea. I got no idea what I'm doing here. I got no idea what's going on. I've gone from being quite reassured I'd nailed the problem to what's going on? What's going on? I know what's going on. Coffee. Well, I haven't been able to figure out anything here. I've checked the resistances of various stuff, these big capacitors here. There's nothing there that's shorted out that I can find anyway. So what I've done is I've disconnected the diode I put in. So now the rectifier and the diode are disconnected. This means I'm going to run this unit with no bias in the Increductor. Is that a risk? It may be. So what I'm also going to do is I'm going to utilize something here I don't utilize too often, and that's this variable power supply here, hidden behind all these wires. Let's take a few off. Okay, down here. This guy here. Switch it to output voltage. So it's set to 117. So it supplies 117 up basically into this box here, which is the dim bulb switch box. So I'm going to cut this way back. It's a fit around 50 volts. Second thing I'm going to do, I'm going to pull the rectifier tube out of here, because that whole part of the circuit is of no interest to us. This is a little isolated piece of circuitry. It appears to be causing the problems. So that'll keep high voltage and the operation of the rest of the unit off, more or less. A little less than more, but at least there'll be no high voltage in there. We're going to turn on the power of the lower voltage, and what are we going to watch? At that point, we watch the dim bulbs. We put the power through the dim bulbs still. I could also switch this to wattage, but I don't know what to expect here. If there's a dead short in there and throw my meter rate over, I don't know. Let's leave it the way it is. So we have 50 volts coming. Will the dim bulbs come on? Did those bulbs come on normal and I just got cold feet and didn't leave them on long enough? Who knows? Okay, so diode disconnected. Here we go, watching the dim bulbs. Okay, no dim bulb action whatsoever. Really operating this thing? I pulled the plug out. Right. Jim, no wonder. I pulled the plug out to do that other test. I get to put the plug back in. Okay, so this time's a little more exciting because it's for real this time. So hit the switch and see if the lights go. What was that? I think that was just a weird coincidence. Some weird sound in my house. My wife's up and active upstairs. I hit that switch, I heard something funny. Okay, hit it again, because I really wasn't paying attention to everything. So no dim bulbs. 55 volts sitting there. Diode disconnected. No current flowing. Okay. So we're going to interrupt the power. No power now. I'm going to reconnect the diode. Incidentally, you might be thinking, you know, when I soldered in there, it was a little tight against the back panel, and maybe I shorted it to the chassis. So shorting it to the chassis might not cause a problem. Well, at least this kind of problem. And number two, no, I didn't short it because I checked it. There's no short to the chassis in the work I did. Having said that now, let's just double check. So I'm looking right behind a particular connection there. No shorts to the chassis. Okay, so power's off. Let me turn the master power to. Okay, we're going to put the diode back on. What's with this diode? Is there something wrong with the diode? The diode is a brand new modern diode, not a NOS. Probably from the around 2005, somewhere in that range. So it's not old. .691 millivolt drop, and IR in nanoamps. That sounds okay to me. The duty this guy is doing is pretty rugged, really, in a sense. That he's not feeding into some hyper complex circuit. It's just running some current through a coil. There's really nothing to it. Okay, so that problem is the possible problem of a bad diode is eliminated. Diode backwards? No, I double checked that and triple checked it and quadruple checked it because I know myself. I like to get these in backwards, but it's not. Definitely not. And then I take. Yeah, okay. Now did I just solder it to the right terminal? Am I doing something dumb there? That's pretty tough to get that wrong. But I have my ways. No, that's correct. Okay, so now we're going to repeat the power test and see what happens with the dim bulb lights. First of all, again, 50 volts only. Nothing happened. Okay, why is that? Why did nothing happen? Nothing at all happened. Power on. Oops. 55 volts. 55 volts on this unit. Switch is off here, that's why. Switch is off. Okay, power down, power on. Try again. There we go. Got some dim bulb action. Now, so we're going to switch this to wattage here. And we're on, I'm going to guess that'll do it. It's a 175 scale. Now the wattage is only accurate if you actually have 117 volts coming out of this. It's not a true watt meter. But we'll see what it does anyway. Here we go. Actually, you know, the lights kind of tell the story, don't they? The lights kind of tell the story. So that came up 175. It came up around 40 watts, just about exactly what this unit is supposed to draw. And that's with no rectifier tube in. That doesn't sound right at all. Oh my God, this is just... Gotta come up with some more ideas here. Wow, it's another hot, humid day outside. So, interesting stuff. Found this piece of paper. Now this has come with all the papers that came with the generator from the previous owners. This isn't so interesting. This is what's interesting, this side of it. Summary of defective spare exchange cable pairs. Well, that sounds like a telephone company engineering situation, doesn't it? Summary of defective spare exchange cable pairs. Exchange or cable number, underground cable, aerial cable, you fill this out, I guess. Up here it says in the form number BT form 949. So BT, Bell Telephone form. Bell Telephone. So what this suggests to me, because I have sheets just like this from the company I used to work for, because I worked for a utility and I have a few of these kinds of things around. This guy must have worked for the telephone company. I think that's what this sheet means. He was probably a technician or engineer in the telephone company. And that's how he would be able to do something like this. Okay, now what am I going to try to do here? So I've looked at, and there's just almost no circuitry here involved in the situation. So I'm going to apply my own DC voltage to this guy and see what happens. I have a number of DC supplies I can utilize here. I'll put a little bit of voltage on and see. We'll put some voltage on and see. Okay, I'll get that ready to go. Okay, not really sure what I'm going to find out here, but this is one way to find more puzzle parts. Go hunting for it. So we're going to, I've turned off the unit, so that opens the switch here, and what else did I do? I turned off the unit. Good, okay, and we're going to feed in right here. So that's the negative side. Oh, that's hard to get at. Negative side. Let's use the negative. Oh, my diode is separated. That's even better. Okay. Bad solder job there. I just tacked it in. Eh? So we'll put power in right where the diode sits. Right where the diode sits. So we'll go. We want the positive to go out the positive side for some reason, and the other one here. Oh, that's very bad. Try it like there we go. Okay, so I'm just putting the power in right there. Switch is open down here. Ooh. Oh. I want to make sure I don't burn out this transformer or this or any of these by doing something dumb. So if I open the switch, I would say it would be no current flow this way, but if I could come down through the windings, get on this wire, come up here, and go right back. Oh, but there's a capacitor there. Should be able to get through the capacitor. So I put power in here, it's going to go up, over, up, through, back down, through these resistors and back to here. Well, it's supposed to. Let's see if it really does. And as long as I keep the current very low, there can't be any kind of real too much of a concern in doing all this. Hopefully. Okay, we're going to use this power supply here. Why, someone's at my door. Okay, now just what we're doing. Put the power in where the diode sits. Current can't flow through here. Flow up this way, maybe through the switch, maybe through the resistor, 15K there. And through another resistor for sure, 10K. So there's 10K in this circuit no matter what. Come up, through this important coil, down, and to get back to here, you can do that. It can come down. I can bypass these. Come down through here. It's going to get the winding resistance, which shouldn't be all that great. Come back up. So the name of the game here is if there's an open circuit, like right there, no current will flow. Okay, so this is a test which, if the test fails, if no current flows, then that could be open, and that's the end of this whole device. That's the end of it, right there. Okay, I should have a drum roll for this. We're gonna keep an eye on this meter. So I'm gonna flip it to milliamps, so it's reading current, but this is a ½ an amp up here, so tiny currents hardly make a difference there. I won't know what voltage I'm putting on it, but this is intended for a very large voltage, so this guy only goes up to 30 volts. Okay, so if I've done this right, this is going to tell a story here. Okay, so I'll flip the current, and I'll watch for the current to go. So you know what I'm seeing? I can see it bump up and come back, bump up and come back. It's charging a capacitor. The current really hasn't changed. Let me flip it right off. Oh, there is a touch of current. The jump there, charging a capacitor. How much voltage have we got on it now? So we got 15, 16 volts. Very tiny current. Hard for me to know on this meter what it is. Let's go a little higher. Where are we voltage here? 20 volts. Okay, so there's some current flowing. That's reassuring. Flowing through leaky capacitors. Bypassing that coil? I can't imagine that. Got a capacitor here. It could be leaking current. The coil could still be open, but I think it'd be pretty tough to leak substantial current through any of these capacitors. That's really about it. So I haven't proven this to be open. I've got a strong indication that it's not open. There's a remote possibility the current flow is going through that capacitor, but that's really, really remote. So there's current flowing in this circuit. Let me operate this switch, and then we should see a current change, because we're going to be taking out 15,000 ohms, taking out almost half the resistance. So it'll be a doubling of current, something like that. And I wanted to operate the band switch, and I don't know exactly which band it is. Maybe it's already shorted out. So we're going to watch this meter again. I got it on milliamps. Let's see, what's the voltage? Still 20 volts. Okay, I'm going to flip the band switch and watch that meter. So one of the extreme settings should cause a variation on that meter. And see anything happen at all. And why would you say that should be a variation? Because in one position, this resistor is shorted out of the circuit. It didn't seem to do anything to the current flow. This doesn't make a lot of sense. What is the resistance between these two spots? You know, I can leave these on. Just plug them into my meter here. What is the resistance? Charging up a capacitor. it's heading for maybe 30 in the end. 30K. A little more than 30K, something like that. So how do you get 30K? If you add 10 and 15, you get 25. That's pretty close to 30 right there. Maybe there's 500 in here. We have these guys involved, although I realize they could be shorted out. Then we have the resistance of this winding in there. These two things are actually in parallel. So the resistance, well, who knows what it is. It's primary resistance. I don't know what it would be. Not that familiar to know that offhand. So 30. Well, okay, I'm going to operate the switch. I'm going to try to knock out this resistor, and we should see a big change in the reading here. Yeah, come back down here. There we go. So I just knocked 15,000 ohms out of this circuit. Put it back. So 15 plus 12 is 27, 28. $29.30. Okay, so what's that proving now? That's proving the switch works, the resistor's there, it goes in and out, or gets shorted out, leading this guy, and the current flow through here. So I think that's pretty positive proof that this coil is continuous. Phew. Phew. Notice I say pretty positive. I'm never on it. Don't ever. I never am 100% sure about anything. That's what's happened to me. That's what's happened to me as I get older. Everything gets gray, fuzzy, and with big question marks all around it. So what's the problem then? What is the problem? Why it's like this is a solid wire type connection all the way up to here, coming back, proven to be carrying current. What exactly can go wrong with this? This bias, it says 65 milliamps right on it. Is that the rating? Or is that the expected current flow? 65 milliamps. That's not a small amount. You know, for going through coils and stuff. So if the only restriction here in the current flow is literally this guy, and that combined, you have 25, let's say 30K, that's what it reads. Well, it reads 28. 30K. What happens if you take 30,000 ohms and try to run 120 volts through it? 30,000 ohms and 120 volts. Well, I think a little factor just came clear to me about how this is working. So, the objective is to put a varying current through here to cause a varying magnetic effect on these coils. And that in turn drives down their inductance. If you put an AC current on here, you've got current going this way and that way, going through zeros. What they've done, I believe, this is what they've done. They've used a bias to cause a steady current flowing through it, and then they interpose or superimpose the AC signal, which they're picking up from the transformer here, selecting how much you want to send forward with this control, and they fire AC on top of the DC. And the result is you never reverse the current, you simply vary the amount of DC, because the two things are going to add, right? So you always have DC going. This is really kind of a bad way to use my finger arrow. You always have DC flowing through it, and you're just varying it at 60 cycles here. So that variation then is carried over. I think if you let this go through a zero, you didn't bias it and have a steady current going through it, you wouldn't get the effect you want. You'd start transforming, in fact. It's kind of surprising that this doesn't transform into here, like the AC power doesn't show up over here. Maybe it does, it gets filtered out. Ooh, I don't know. Okay, that doesn't help me though with this very stupidly simple circuit that I cannot get a grip on it anywhere. You're probably yelling at me, well, just change these stupid capacitors, get them out of there. But all the tests I've done indicate they're not the cause of this. Well, I've kind of reached the end of the road here for what I know what to do, so I'm going to go ahead and I'm going to change these capacitors here. I think I've got replacements for them all. Here's a clunky, dirty old 0.25, but it tests perfectly fine. So this is probably going in to replace that, even though this is just as old as that. This might even be older. But it tests good. I'm going to test each one as I go and do all that kind of stuff. Oh my gosh, but it's past lunchtime now. Okay, got another test. Thought up another test. So this is now a current meter, and it's going to read the current flowing right through that diode, right here. The diode is, I desoldered one of the leads so it's open, so I put clips on it, and I'm going to run power through the meter. We'll see really what kind of current. Now I did do that little calculation I mentioned about 30,000 ohms, 120 volts. What do you get? You get about 4 milliamps. So if that's all correct, then this coil is looking for 4, 5, 10 milliamps, something like that, to do its business, and not much more. So so we're ready. So plug this guy in. And we're still on low voltage here. Where are we? 50 volts maximum. Okay, so I'm going to put the power on. The switch is off here. Just looking around my shop. Am I doing something crazy? Don't think so. Power on, nothing should happen. Okay, switch on, power on. Oh my gosh! Okay, power off right away. Well, that looked like 160 milliamps going up. That didn't sound like 4 milliamps, or look like 4 milliamps. I still got my calculator here saying 4 on it. That kind of current, that's with reduced 50 volts only. That's so clearly something's going on. And it could be a, as much as I really tried to prove all three of these big capacitors to be okay. There's only one here that can really cause this short circuit effect. That's the 40. So this is the 40 here. This is the 40 here. So why don't I just separate a lead and repeat the test? That would mean the current would be shooting through here. So assuming everything's okay, cut this lead, then we won't see this huge current here. But it won't be filtered very well. But what will that matter? Will that really matter? Just probably reduce the effective voltage at this point. Let's try it. Got the lead. Cutting here. So obviously I'm on my way to replacing this capacitor here. Oh, the sound of a wire being cut. Okay, capacitor stick out. Let us test the capacitor before we go any further. Just to see, now that it's free, we'll use this big tester, or small tester here. What's it say? "50 microfarad, 2% loss." That's fine. 50 microfarad, 50, and it's supposed to be a 40, isn't it? Isn't it a 40? It's a 40. 40 measures 50. Usually when these measure high, it means they're a little leaky, but not guaranteed. Well, that looks like this isn't going to affect anything. Well, let's go ahead and give it a try. 200 milliamps. We're all ready to go. I don't think I'm doing anything stupid here with anything. Power on and watch. Okay, Hey. Hey. Ooh, I almost got a short circuit here. No, these are plastic covered. I'm going to clip that back in. This doesn't seem possible to me. Okay, so I've clipped it back in. Let's give it a shot. Here we go. Holy smokes. Well, there we are. There it is. A capacitor that over and over I have tested this capacitor and found it to be okay, along with all its brothers here. So I'm gonna knit this one right out, and we're gonna give them the works. Come out of there. Nice, shiny, beautiful looking capacitor. It says 40 microfarads, 150 volts. So we're going to put it on our capacitor checker over here, a proper, I shouldn't say proper, one that's more suitable for these old guys, these old polarity, right? It looks like negative to me. What we're going to do is we're going to stick 50 volts on this capacitor, whose actual rating is 150. Okay, if you haven't seen this done before, you see the eye is slightly open, or it's open here at the bottom. So what's going to happen is I'm going to apply the voltage. Current is going to rush into this capacitor, well, maybe rush into this capacitor. The eye will close while the current flows, and then the eye will open. If the current capacitor is really in good shape, it'll open just like that again. If it's not, it won't open, or it'll only open partially. Okay, ready? Here we go. And she opens right up. But that didn't look like any 40 capacitor. That went pretty quick. Let's put 150 on it. This is its rating. Okay, so it's a higher voltage driving more charge, taking about the same length of time to do it. Now we're going to let it discharge for a bit. So how could hooking this up cause that wild variation in current? We'll try measuring its value here. I'm just letting it discharge a little bit. Okay, I think we can try it now. So it's supposed to be a 40, so it should be on this scale here. And we turn this until the eye pops open. Okay, so it's a pretty clear place, and it's right in mid scale, so this is probably quite accurate. So we'll get it open right there. And on the 0.1 to 50, here's the 50, we are reading 3 microfarads. Oh, this is supposed to be, it should be way up here. Okay, so it looks like 3 to 4 microfarads on this guy. Let's try a different test here. Let's go back to that other 3 to 4 microfarads. What did this one say? Discharge capacitor before measuring, and I really didn't discharge as much as I could have. 50. Am I reading that other meter wrong? 50 on here. 50. 50 is kind of believable. 4 is not really believable. Let's try this again. Oh, I'm on this scale. Or did I move this? Maybe I had it in the wrong scale. I was reading it wrong. Okay, on the positive end, Jim. 4 is just not. Okay, we go hunting now. That's popping open here. It's the same reading as on the other meter, 50 something. Capacitor is fine. This capacitor was good enough. I'm pretty sure it's good enough. Good enough. Removing it was a waste. But wait, how can that be? Because when I hooked it up, wow, this just does not add up. Am I going to put that same one back in there? Hey, let's try this other one. Let's try this other one. Let's see what happens. So this one is a 0.25. This is headed some. This is for another purpose. 0.25. Let's check it out anyway. Why not? First, we'll read its value. 0.25. I think it's going to be in this band here. We're on the. No. 0.25. No, it's going to be here. 0.25. Something there. Right there. Right here. We're on the 0.5 scale. So that's 0.1. That's 0.5. That'd be 0.225. So it's right on the money. It's an old, ugly looking thing. It's a good capacitor. He's probably going to replace this one. Oh my gosh, how is it that happened? I don't understand. I took this out of the circuit, current dropped way off. Put it back in, current through the roof. It's a mystery that's going to have to wait till tomorrow, because now it's pushing 1 o'clock here. I'm very hungry. And, yeah, I'm going to stop here. So, well, thanks a lot for watching to this point. Boy, oh boy, what a head spinner this thing is. Fun. See ya.